Welcome to Efiwe, excellence without stress.
Hi guys, and welcome to Efiwe, excellence without stress. In this section of the study, we are going to be considering chemical bonding and shape of molecules. Before we get into that, it's important to note that the reason we talk about chemical bonding is simply because we have that most of our elements do not have completely filled outermost shell. Take for instance nitrogen. So if you consider nitrogen has 7 electrons. So 1, 2, 3, 4, 5, 6, 7. So notice that the outermost shell should be octets and it will need 3 electrons to fill it. So it does 2 things to get these 3 electrons. It's either it completely removes the 5 electrons so that the outermost shell will now be this completely filled innermost duplet shell, or it accepts 3 electrons. So it can either accept these 3 electrons by sharing or by complete transfer of electrons. So you notice that basically that this is the reason we talk about chemical combination, to bring the elements to their completely filled outermost shell state and then make them to become stable. Because when the outermost shell is completely filled, the element is said to be stable. So with that said, we are going to be considering 2 types of chemical bonds. The intramolecular or interatomic bond is the type of bond that exists between atoms in a molecule, while the next set of bonds are the intermolecular, which exist between discrete molecules. What then are your examples of your intramolecular bonds? You have your electrovalent bond. So talking about your electrovalent bond, major points to note about the electrovalent bond is that it exists between ions. Yes, electrovalent bond exists between ions. The second point to note about the electrovalent bond is that it involves complete transfer of electrons from your most metals to your non-metals. So in most cases, the metals are the ones transferring electrons. They will lose the electrons and the non-metals accept them. So if you are to consider something like sodium metal basically has the shell configuration of it has 11 electrons. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have 11. Then we consider another element, chlorine, which is a non-metal. Chlorine has 17. 1, 2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So notice that in this case there are 17. Now for the metal, you will notice that the metal has 1 electron in the outermost shell. So if it is going to be complete, it would either accept 7 or lose 1. Preferably to prefer to lose 1. In the case of the non-metal, it has 7, which means for it to attain the octet state, you need to collect 1 or lose 7. So it's easier for it to accept 1 for the non-metal. But for the metal, it's easier to lose the electron in the outermost shell. Hence, you are going to have a transfer of this to this. And when that occurs, you will now have a new product where you have sodium ion. I'm going to only put out this. There's no electron in the outermost shell. And then in the case of chlorine, it is now joined to it. So them being joined together would form the bond. In the case of chlorine, its outermost shell will have 1, 2, 3, 4, 5, 6, 7. And then that 1 electron that was transferred from sodium here. So this is the new compound form. And the bond existing between them is electrovalent. So mind you, electrovalent bond is a form of bond that exists between ions as a result of complete transfer of electron from the metal to the non-metal. So that's that basically about the ionic bond. Now, when you have an ionic compound form, ionic compounds do not occur as discrete molecules. They are just aggregate of ions. So Na plus, Cl minus, another Cl might be here with another Na here. There's no particular sequence or structure it has basically. The compounds that have discrete or particular structures are what we refer to as your covalent compounds. So that's that basically. We go to the next one. The next type of bond is your covalent, and there are 2 types of covalent bonds. The first one is ordinary covalent bond, while the second one is dative covalent bond. So illustrating to differentiate between the 2, when you talk about covalent bond generally, as I said in ionic, it involves complete transfer. You are moving it from here completely to the other one. But in the case of covalent, it involves sharing. So think sharing. So things to note about covalent bond is that number one, it involves sharing of electrons between non-metals. So covalent bond exists between non-metals. It doesn't exist between a metal and a metal. Neither does it exist between a metal and a non-metal. Between a metal and a non-metal, you have your electrovalent or ionic bond. Yes, ionic bond is the other name for electrovalent. But once you are dealing with your non-metal and your non-metal, once you see two non-metals joined together, just know there is a covalent bond there. Just have that in mind. Two non-metals joined together to form a compound, non-metal. Exactly what is going to give is your covalent bond. So once you see H and Cl, two non-metals, so covalent, CO2, two or more non-metals, covalent, CnH3, still covalent. So let's describe what we mean. As we said, it involves sharing. So if I'm considering, let's say for instance, I'm considering a bond between two hydrogen atoms. Hydrogen has one electron in the outermost shell. Another hydrogen has one electron. If they are going to form a covalent bond, non-metal, I told you once they are forming a bond, is going to be, you have hydrogen here, and then you have another hydrogen, and then the two of them will now have this particular electron shared between the two. So have that in mind, that they join forces such that if I add this hydrogen, how many electrons do you now have? It can say 2. If I add this hydrogen, it can say 2. Now note that for hydrogen, the outermost shell is filled with only 2 electrons. Okay, let's consider another molecule. Imagine you had a molecule of hydrogen fluoride. Hydrogen fluoride. Hydrogen has 1 electron in the outermost shell. Fluorine has fluorine is 9, so it has 7 electrons. It's in group 7, so it has 7 electrons in the outermost shell. Because of that, when they are to form a molecule, remember, non-metal covalent bond, which means sharing. So if they are going to form this compound, you are now going to have that the new compound form would now have hydrogen bound to fluorine. But then let's consider the electrons. You have that fluorines 1, 2, 3, 4, 5, 6, 7, and then hydrogen brought 1. So notice that these 2 electrons are going to be shared by both parties. Now if you ask fluorine, how many electrons do you have? It will say 1, 2, 3, 4, 5, 6, 7, and 8, because it is sharing with hydrogen, so it's 8. But if you ask hydrogen, it will say 1, 2, which means it is sharing with fluorine. So notice that they have completely filled shells, even though you are dealing with a sharing. This is what we refer to as ordinary covalent bond. So in ordinary covalent bond, it is a form of bond that is formed between non-metals, which involves equal sharing of electrons. So the implication is that if hydrogen brings 1, fluorine brings 1. If hydrogen brings 2, fluorine brings 2. Once it is equal sharing, it is your ordinary covalent bond. In a situation where you now have unequal sharing, it becomes dative. So dative covalent bond is a form of covalent bond in which involves sharing of electrons, but then only one of the combining atoms brings the shared pair. So consider something like an ammonia molecule. So this ammonia molecule has a lone pair of electrons. A lone pair of electrons is a pair of electrons that is not involved in the normal covalent bond. This pair of electrons formed between nitrogen and hydrogen is the shared pair. So you refer to this as the shared pair. And the bond between equally shared pair is what we refer to as covalent bond. Okay, but then this one that is left alone after sharing has occurred is referred to as the lone pair. Now, this lone pair, if it is now shared with an empty shell, so imagine you had a situation where ammonia decides to form ammonium ion by combining with hydrogen ion. Hydrogen ion does not have any electron, but it needs electrons to become completely filled. So what does it do? It joins with ammonia. So joining with ammonia, ammonia will now have hydrogen, hydrogen, hydrogen. And then ammonia will contribute this shared pair. It will bring this shared pair so that hydrogen will share from it. And when hydrogen shares from it, you will notice that eventually it becomes stable. So a form of sharing in which only one of the combining substances contributes all that was shared, it is referred to as dative covalent. So this is dative bonding, or you say coordinate covalent bonding. So if it is equal sharing, it is ordinary. But when you have one of them contributing the shared pair, it is referred to as dative covalent bonding. Okay, having said this, as I said, the important thing to note is that it occurs between non-metals for your ordinary covalent bond. Now, the next set of bond is the intermolecular bonds, and there are majorly two major parts. You have the van der Waals forces, which is separated into two. London dispersion. Now, London dispersion occurs between non-polar molecules. So once you notice a non-polar covalent molecule, the forces between them is your London dispersion van der Waals force. And your non-polar molecules basically have the same terminals. So if you have a molecule that has the same terminals, like in hydrogen molecule, you have the same terminals, which means that this is non-polar. In your carbon 4 oxide, which is linear in shape, the same terminals. It means that the charge here is equal to the charge here, so it's not polar. If it is polar, you have different terminals like HCl. You get. So in this case, you have that once you are dealing with non-polar molecules, the intermolecular force between a CO2 and another CO2, that's what intermolecular means, between a molecule and another molecule. The force between two CO2 molecules is your London dispersion van der Waals force. So once you think non-polar molecules, think London dispersion force. Okay, the next one we're going to consider is your dipole force. Your dipole is the one that now exists between your polar molecules. So if you have HCl and another molecule of HCl, the force between them is going to become dipole. So here you have London dispersion van der Waals, while here you have dipole. Okay, then finally, the next force we are going to talk about is the hydrogen bond. The hydrogen bond is the strongest intermolecular force. That's the first thing you need to note. And it occurs between molecules containing hydrogen and nitrogen, oxygen, or fluorine. Please note, I said or, which means either hydrogen and nitrogen, or hydrogen and oxygen, or hydrogen and fluorine. So between molecules that contain those combinations. So if I have a molecule that contains hydrogen and fluorine like hydrogen fluoride gas, if I have another hydrogen fluoride gas, the force between them is the hydrogen bond. So yes, this is polar, but then specifically, this is a different type of bond. It's not the dipole. Dipole occurs between normal polars. But if the molecules contain hydrogen and fluorine, hydrogen and oxygen. An example of a molecule that contains hydrogen and oxygen is water. So between two water molecules, you have your hydrogen bond. And then the other elements hydrogen combines with to form a molecule that is involved in hydrogen bond is ammonia. So nitrogen and hydrogen combining to form ammonia, nitrogen and hydrogen. So if you have two ammonia molecules, you have hydrogen bond. And as I said, it is the strongest intermolecular bond between covalent molecules. Finally, we are going to talk about popular shapes of molecules. Water has an angular or V or bent shape. The reason this occurs is that whenever you have a molecule, and that molecule is made up of three atoms where the central atom has two lone pairs, it basically leads to the formation of your angular, that is basically called trigonal planar structure. So you have that in mind, that the angular structure can also be referred to as your trigonal planar structure. So central atom is oxygen, and that central atom has two lone pairs. Automatically, it forms this angular structure. So three atoms where the central atom has two lone pairs will lead to the formation of your angular shape, which is also referred to as the V shape or the bend shape, or you refer to it as your trigonal planar structure. The next structure we are going to be considering is that of your silicon tetrachloride and methane. So all molecules that are made up of 5 atoms, in which each central atom has no lone pair of electrons, is tetrahedral. So if you notice that you have a molecule and there are 5 atoms in the molecule, like SiCl4. So notice this, 5. This is 1 silicon and 4 chlorine. And then the central atom is silicon. Silicon has 1, 2, 3, 4 electrons in the atomos shell. So it has no lone pair, which means chlorine will bond here. Chlorine will bond here, Cl. Chlorine will bond here, Cl. Another chlorine will bond here, Cl. And then another chlorine will bond here, Cl. It basically implies that you are going to have a tetrahedral structure. Once one of the central atom does not have a lone pair of electron and there are 5 of them, 1 central and 4 surrounding, the implication is that you are going to have a tetrahedral structure. Methane too has that tetrahedral structure, basically, as a result of this same reason. Carbon has no lone pairs, and then it's basically surrounded by 4 other atoms. Hence, you have a tetrahedral structure. The next one is that all diatomic molecules are linear. So every molecule that you notice is diatomic is linear. Once you have 2 atoms in a molecule, HCl is linear, HF is linear, oxygen gas is linear, nitrogen gas is linear. once you have two atoms between a molecule, you are talking about two atoms in a molecule, the structure is going to be linear. We also have that carbon 4 oxide gas is linear, basically, and that is exactly why it is non-polar. It is made up of different elements or atoms of different elements, but because of its linear shape, it is now non-polar. Okay, then we go to the next one, which is that all molecules made up of 4 atoms with this central atom possessing a lone pair has a trigonal pyramidal structure. Hence, ammonia and phosphine have a pyramidal shape. Now, what this means is this: if you have 4 atoms and then the central atom has at least one lone pair, the implication is that you are going to have a pyramidal structure. Phosphine too has a central atom possessing a lone pair, hence is going to lead to formation of a pyramidal structure. So this is basically what we are going to be studying through this particular section. Thank you very much for studying with us.